Good. Thank you. Recording started. So good morning again. Let me just give you two very minor information. The exams are published. You should be able, the dates, you should be able to see them on Alma Esami. And you, of course, are not yet able to subscribe to the exam for the reasons that I mentioned to you. Subscriptions will start on May 2nd. I think I fixed the date of May 2nd. And second information, some of you pointed out that during the lectures in physical presence, some of you had some issues by the blackboard because it was too small. So there might be a couple of reasons for that. If you see the blackboard very small, maybe because the camera is set with the wide angle, and in that case you see the whole room with you see also the heads of some people and the blackboard very far. In this case, if I am using the blackboard, it means that I simply forgot to change the camera. So if you experience an issue like that in the lectures on Monday, just please step in and ask me to change the camera. There might be a second issue. When I use screen sharing and the blackboard both, you may have some problems because you see the screen sharing very large and the blackboard very small. So in this case, I think you have the opportunity to pinpoint the blackboard, to enlarge the blackboard, but I am really not sure. So I will, let's try next time. If you have an issue with the blackboard, please step in, whatever is the problem that you have, and let's try to resolve it, okay? Because otherwise, if there is a last solution, which is the fact that when I use the blackboard, I stop screen sharing, but actually I would like to keep both of them. I hope it's clear. And of course, this issue is not for today, because today I'm teaching online. It's just for Monday's lectures and only for some of you. Okay, good. Now, what are we supposed to do today? We just finished to discuss on risk. Actually, we have not finished the discussion because we will have some more thinking, some more reasoning on risk estimation during the progress of this course. But let's say that the main theoretical part is done. And I have, of course, other lectures to move forward, but I thought that it would be a good idea maybe to make an exercise on risk estimation. So this is my plan for today, to make an exercise all together. And sorry if I didn't tell you in advance that today was dedicated to an exercise, but on the other hand, it's an exercise with a strong connection with the theoretical part. It's an exercise that, in my mind, should help you to understand what we did, and maybe to get more familiar and more used to the concept of risk estimation, probability estimation. So let's try. It will be interesting because I prepared the exercise indeed by making reference to a real case, but actually we are using synthetic data. I prepared the exercise and I didn't develop the exercise myself before presenting it to you. So it will be the first time also for me. So let's see what comes out. And I think it will be interesting because by making a practical computation, which is not difficult, I think, you realize what are the problems, and I think that you better realize the concept behind what we are trying to do. Let me share the screen and go to my website now. Okay. Let me just, okay, you should see my website. If for some reason you don't see the screen, because I am using a Teams version that doesn't put the red rectangle around the screen that I share. So if you don't see the screen for some reason, just let me know. Let me log out, because otherwise you see the website in a different form. Okay, so climate change adaptation. Oh, let me just go back a little bit, just for a moment, to risk-based adaptation design, the lecture that we just finished. And I just want to tell you that we are using this formula in the exercise that we will elaborate together. R, the risk, is given by probability times vulnerability times exposure. So this is the formula that we will use. And let me show you the last figure, this one, which I presented to you. This is a graph of vulnerability and exposure for an hypothetical case study. Vulnerability is in red, exposure is in blue, and R is the risk computation. Here you see on the vertical axis exposure, vulnerability, and risk. On the horizontal axis, you see the intensity of the event. I wrote intensity because this refers to a very general event. So it may be an earthquake, maybe a flood, maybe a drought, whatever it is, okay? Because our focus is very general. It is true that we make a special focus on water, on water-related risks, but our focus indeed is general. I am frequently making the example of the earthquake, which is, as I repeatedly said, it's not directly related to climate change, but it is, I think, a nice case of a threat that is highly considered today, especially in the Italian context. And so I think it is a nice example because it also emphasizes the importance of probability. You know that we describe earthquakes basically probabilistically. For other events, we may also describe them with more, let's say, physically based mathematical models. For earthquakes, I think the example is nice because indeed seismic engineers are used to deal with earthquakes through probability. Okay, so I just want to say before I move forward to the exercise that here in the horizontal axis, as I said, there is the intensity of the event. I could also put on the horizontal axis the probability because for a given intensity, I can associate a probability. So you may see this graph, which I call PIVR curves, PIVR because it stands for PEVR. You may see this graph with the intensity of the event like you see on the screen on the horizontal axis, but you could see also probability there, or return period. Keep in mind the concept of return period because when we talk about climate change, it's a synonym of probability that is largely used, as I said. Good. Now let's see the exercise. It was just uploaded in has a link in my website. Let me go back one page. And if you see here under exercises, there is an additional link, the one which I'm pointing to with the mouse. Let's click on it. I just want to say, you know, that these links are provisional, so they are evolving. For instance, the next one exercise, I remove the link because it is, I substituted it with the exercise that I'm proposing to you today. Given that this is the first time that I deliver this course, you know, while I progress, I also look at your eyes and I make changes. Okay. And of course, if you have any suggestion, any criticism, you have to step in and tell me, okay? And if you don't want to step in, send an email. So computation of risk associated to flood events. This is the exercise. It's a download link. So if you click on the link, you get a zip file. Let's open the zip file, and you see that there are two files. There is a text file. Let me open it just to have a look with only numbers. 1 second, double click. Yeah, this is a text file with only numbers. Okay, these are the data that I need to make the computation. Let's close it and let's look at the PDF, which is a text of the exercise. So everything is new here, was prepared just yesterday and today in the morning. So you may see mistakes, spelling errors, whatever you think it's awkward or strange, bizarre, just let me know, okay? So exercise, computation of risk associated to a flood event. So we make reference to a flood here, and let's read the text. We have annual maximum peak flows for a river. So a river, of course, we are talking about floods from a river in this case, and our information, our data are annual maximum peak flow. What does this mean? It means that every year you have a monitoring of the river flow, okay, how much water passes along the river, and every year you pick the max value. This is a typical approach in engineering. When you want to associate probabilities to floods, we follow this approach. We refer to a record of annual maximum peak flow. Okay, we don't go into the details, we don't discuss why, and it is just a way of making a synthesis of the information. Okay, so it means that you want to reduce the numbers to analyze. So let's suppose that I have an observation every minute. I have millions of numbers. I focus only on the annual maximum peak flow. There are other methods of analysis. Just 1 second, because I got a beep. I want to make sure that nobody is in the waiting room. Okay, very good. Nobody's there. Let me just close here. Good. So annual maximum peak flow is expressed in cubic meters per second. The river flow is expressed as volume of flow that passes through the river per unit time. So volume divided by time, in this case, is cubic meters per second, okay? And these annual maximum peak flows were observed for a period of 150 years. It means that I have 150 numbers to analyze, okay? And these numbers are reported in the text file maxan.txt, which is the text file with the numbers that I just opened a few minutes ago, okay? Good, so our analysis is only based, our computation of probability is only based on these 150 values of annual maximum peak flow. Just please make sure that you understood what the numbers are, because in any case, in general, when you analyze numbers, we make reference to a physical event, to a natural hazard. Climate change is a component of the nature system, is a process which develops, which is included in the Earth system. So usually we make reference when we analyze numbers to an Earth system process. Just make sure that every time you analyze number, you understand the meaning, because if you understand what the numbers are, you will see during this exercise, it's difficult for you to understand the meaning of your results. This is trivial, but I can tell you many times, especially when talking about climate change, people talk about numbers also in the media, in the television, and it's clear that they don't understand what the numbers are. They don't have the perception of the meaning. Okay, this happens very frequently. So the suggestion that I'm giving to you is not trivial. Okay, and if it's not clear to you what is an annual maximum peak flow for a river, please step in. Let's discuss. It would be very interesting. Okay, so we also need. Why do we need these numbers? To estimate probability of the flood. So I need flood observations, and you know, the annual maximum peak flow is supposed to be something that is representative of floods, I need these numbers to estimate the probability of the flood. Good. Now, I also need information on vulnerability and exposure. And a very simple approach is taken here. So there is written, the river is protected by levees so that vulnerability is kept to 0 up to a river flow of 12,000 cubic meters per second. Then vulnerability is increased linearly to 1 for a peak flow of 18,000. So let's look at the graph. This is on the left, the graph of vulnerability. These graphs are done with R, by the way, very quickly. So you have, as you see here, the river flow in the horizontal axis and vulnerability in the vertical axis. Vulnerability is 0 up to 12,000, and then there is a linear increase up to vulnerability 1. You know that 1 is the max of vulnerability. Vulnerability is varying in the range 0, 1. And vulnerability 1 is reached for a river flow of, I think I said, 18,000, okay? And then the exposure of the flood prone area is null up to a river flow of 8,000 cubic meters per second. Here there is a subscript that I forgot. Then exposure increased linearly up to a value of 12 million euros for a river flow of 16,000 cubic meters per second. Okay, good. Now, compute. This is what we need to do. Compute and plot in a graph the risk associated to flood events for peak flow ranging from 0 to 30,000 cubic meters per second. Now, the last sentence, it is very important. Compute the risk by the relationship that we know R is equal to P times V times E, where P is computed with the log normal probability distribution. We will see that it is very easy into R to compute the probability with the log normal probability distribution for any value of the river flow. This is trivial, okay? For each peak flow, this is important. For each peak flow, use the probability of not exceedance to estimate P. This is something that we didn't discuss in detail. Okay, we know what is the probability of not exceedance. We also called it cumulative probability, but we didn't talk about using it into the risk estimation. In fact, here, the last sentence says, make a reasoning on the meaning of the obtained risk values. What do they mean? Because when we discussed risk, I just said use probability in the formula. In the formula here, use probability, okay? And I made reference to the probability of rolling a dice, associated to rolling a dice, tossing a coin repeatedly. I didn't say what we have to do when the intensity of the event is a real number. I said that for a real number, I need to resort to the probability density to estimate cumulative probability. But I didn't discuss with you what probability should I plug in into this relationship here when the intensity is a real number, like in this case, the intensity of the flood is given by the river flow. So now I am proposing that here you put for any river flow the probability of not exceedance. But then let's make a reasoning on the meaning of the obtained risk values. This is the fundamental contribution of this exercise that brings us to discuss in practice what is the meaning of the results. But first, let's get the results. And it's quite clear how we have to get them, because here we have a formula that is very easy to apply. We have to plug for P the probability of not exceedance of any river flow from 0 to 30,000. Of course, we will make a discretization of the range. And then vulnerability and exposure are given by these two graphs. It is quite simple. Okay, the only complicated thing is to use the log normal probability distribution, but we will see that it's not a big issue. Okay, I'm proposing to make it in R because it's much simpler. And also in Excel, you have the means, the functions for applying the log normal distribution, computing probabilities with the log normal distribution. But into R, it's definitely much easier, okay? But sorry, I didn't turn off the phone. Just 1 second. Okay, good. And let me just make it silent. Good. Okay, so at this stage, I think we can open our window. So in my case, it's already open. This is my R terminal. I suggest that you make the exercise with me, but you can also follow if you don't want to repeat it. It's not really a problem. Let me just change the font. I want to make it larger. Here it is. Just 1 second. Here it is. 25. Okay. Okay. Good. Now, the first thing that we have to do is to upload the file, to upload the maxan.txt file. Okay. It is into a zip, if you remember. So what we have to do is to extract the text file from the zip and put it in your document directory. And in order to do that, let me just show you, let me download it again. If you click on the exercise, on the link of the exercise, you get your zip. If you click on the zip file that you just downloaded, because when you click over the link, you will see in your screen that you get an alert that you downloaded the zip file, and you can click on it. And then you see these two documents. Now, the text file with the extension txt should be placed in your document directory. And I assume that you are working with Windows. If you're working with a Mac, you can put it over the desktop, okay? And in order to copy it in the document directory, you can click on with the right, there is extract, and then I put it in my document directory. Of course, what you see on the screen, on my screen, which is operating on a Linux environment, is not what you see in your Windows, okay? And I am just putting it in my document directory. Let's try. Good. I give you a couple of minutes to do that. In order to check if everything went fine, you have to go to the R console and try to scan it. So I try. Let's call the variable the vector. Let's give to the vector where we will put the data the name max one. And you have to use the function scan and then open the round parentheses, as you see on my screen, open the comma, and start typing the name of the file, like MA, and then you press on the tab key, and it should complete the name. I go back. Now I'm just pressing the tab key. Okay. And then I can close the parentheses, the round parentheses. I type enter, and you see read 150 items. Good. I wait for a couple of seconds. If you have any serious problem, please step in. Okay. Serious problem means that you want to replicate what I'm doing, but for some reason you can't follow me. If you decided not to replicate, it's not a problem. Absolutely, just wait. But if you decided to replicate and you can't, let me know. Just let me look at the chat. I want to make sure that I'm not missing anything. Okay, good. Let me see how many people are here. 28, okay. Let's make a plot of this. Okay, plot maxan pipe equal line. Here is the plot. Why did I make the plot? I told you several times, I made it because I'm making it because every time that I deal with numbers, besides understanding what the numbers mean, I need also to check if the numbers are meaningful. I can only check if they are meaningful after understanding what they mean. Okay, so these are annual maximum peak flows, and you see that it looks like they are fine, meaning that you see there are some peaks, some outliers, which is fine with the river flow process, with flood processes. You don't expect a big flood every year. In general, the series is quite regular, but we have these spikes, which are not so, I mean, they are not very, it's not very spiky. Let's suppose that you got something different, like, that's just to make fun of it, to plot the exponential of it, okay? Exponential, of course, it's not, so let's plot the square of it. Just to show you something that is not reasonable. Let's look at the plot. You see that this is already a bit strange because there is, you see that if you look at the normal values and the spikes are more than 3 times higher than the normal values. It may happen for a river, but it is a bit too much, especially for these values of river flow. But this could be still reasonable. If I found a graph like this, I would try to understand if the river provides the motivation for getting a flood that is occasionally 3 times higher than a normal flood. Okay, still reasonable, a little bit hard to believe, but still reasonable. Let's elevate at the 4th power. This is not very reasonable. Here you have almost, I would say, there is an order of magnitude of difference between the normal floods and the spikes. This is not very reasonable. Okay. It may happen sometimes that you get outliers from observations of natural events, and these outliers indeed may be caused by measurement errors. So we have to be careful to measurement errors because the computation is completely false by measurement errors if they are relevant, of course. Let's get back to the original graph. This is more than reasonable. Okay, let me have a look at the chat. If there is something wrong with you, I would say that you are happy. So let me try to move forward.
Prof?
Yes, please.
What is type 1?
It's not a 1, but it's a L, and it determines the type of the graph. Let me just show you. If I put P, you get points, and if you put both, you get both of them. Is this clear?
Yes, thank you.
Okay, very good. I think there are also other options like squares, let's inspect this. If you call the help of plot, there is type here, you see, P for points, L for lines, B for both, C for the lines part alone of both. Let's see what happens if we use C. And O is for both overplotted, and H for histogram, S for stair steps, etc. N for no plotting. This is interesting. But let's try to what happens with C and O and H. So now we have here both. If I use C, see the difference? I don't really understand. Overplotted. I don't. Okay. Probably they are overplotted, but in this case with the white color. So it is something I wouldn't use in this form. But let's try the others, because O, I think, was another one. This is points overplotted. It means that the lines are not broken up within the points. We also have other options for giving the size of the line, the size of the points. Let's don't go into the details. And the histogram, which is not a good idea in this case, is this one. It's not a very good idea. I don't think it is very clear, but still, it may be an option. And also we have, as I said, other options for the colors, etc. Okay. For instance, here, if I make col equal red, I should get the histogram in red. Okay. Let's move forward. The plot is fine. Now, what I have to do is let's remember what I have to do. I have to compute the risk for any river flow from 0 to 30,000. Let's assume that we span the range with a river flow step of 100. Okay, so we don't compute for any real value of river flow from 0 to 30,000 because I would need to make an infinite number of computations. But if I get a step of 100, it means that I make the computation for river flow 0. It's meaningless, but I can do that. 0, 100, 200, 300, which means that from 0 to 30,000, I need to compute, to make the computation 300 times. When you use a code, it doesn't really matter the number of computations. So 300 is just one, it's just one cycle. I could use also a shorter delta, a shorter river flow step. Let's take 100, okay? So let's create this vector of river flow. And so let's write river flow. It's equal to sequence. This function sec creates a sequence in R, and you have to give the first value, comma, the last value, 30,000, and the step. In this way, we should get I think 300 plus 1 numbers. Let's see. This is river flow, and let's compute the length of it. Yeah, it's 300 plus 1. And if you look at the numbers, you can just type it on the screen. You see, you get the whole sequence from 0 to 100, 200, 300, 400. This is quite straightforward. Let me clear the screen and show you again the instruction. Okay. This is the instruction to generate the vector. For each of these river flow, I have to compute exposure, vulnerability, which is easy, and probability. Let's compute the vector of probabilities, which is probably the most difficult one in conceptual terms, okay? Exposure and vulnerability, they are not really straightforward because I have to make an interpolation of the functions that I have here. Just 1 second. I have to make, let me show you. I have to make an interpolation, but it is conceptually is straightforward, okay? Okay, let's focus first on probability. How to compute the probability for this vector of river flow? I have to use the log normal distribution. Fortunately, into R, I have a set of functions which allow me to deal with the log normal distribution. The log normal, I just want to remind you, we discussed it on Monday. It means that if I take the logarithm of the river flows, they are distributed according to the normal distribution. So the log normal is very easy. It is just the normal distribution applied on the logarithms. Into R, I don't need to make all of these steps, compute the logarithm and then apply the normal distribution, because I have a set of tools that allow me to apply directly the log normal distribution. Okay, and how to let's see how I can do it. And as I said, I have a set of tools, and let me just show you. You can call the help for PL norm, which means probability log normal. And if you call the help for this function, you see that the help says the log normal distribution. And what you see here is density, distribution function, quantile. Let's forget about quantile for now, and random generation for the log normal distribution. So I would say that we have to use this because it's the probability. D is density. I'm not interested in the density. I need the probability of not exceedance. So let's focus on this one. Q means quantile. In principle, we don't know what it means, so let's forget about it for now. We just realized that we don't have to use this function here. R stays for random generation. I'm not interested. This is the function that I need, okay? And basically, what I have to do is to use, as I said, this function, but I have to understand what the arguments are, okay? So here I have the first argument without default value. I need to understand what is this Q. I'm trying to select it, but actually it doesn't work into R, and you just see that Q is in blue now, very, very close to black. And then I have a second argument for which I have a default, it's min log, and a third argument for which I have a default, which is SD log. Let's forget about lower tail and log P equal false. These have defaults. Let's forget them, okay? So what is Q? Let's see. Q, it says this is a vector of quantiles. What is the quantile? At this stage, I think I have to tell you. These are the river flow data for which I want to compute the probability, okay? So let's just take for granted that here I have to put, instead of Q, my vector river flow, okay? The quantiles are synonym of observations, not really observations. Let's say river flow for which I have to compute the probability, okay? Good, so I have to put river flow here. And then for any value of river flow, it will give me the probability of not exceedance, okay? Now, what is mean log? Is the mean of the logarithm of the data. And standard deviation SD log is the standard deviation of the logarithm of the data. So what values should I use for them here? remember this log normal probability distribution, we use it to fit our observations, the 150 numbers. We use the log normal probability distribution for describing the probability of river flow, which is in turn described, the probability distribution is described by my numbers, by my annual maximum peak flows. So if I want to make sure that the probability distribution correctly describes my annual maximum peak flow, what I have to do is to plug into mean log the mean of the logarithm of my data, and in standard deviation log the standard deviation of the logarithm of my data. The mean, you know what is, okay? It's the average. The standard deviation is a statistic that describes the variability of the data. And you may have heard of the standard deviation several times, because when people make pools, usually they give you an average response, and then they say there is a huge standard deviation, meaning that the opinions are very different. So standard deviation is an indicator of variability. The mean is an indicator of the tendency, the central tendency of the data. And the standard deviation is the variability. Okay, good. Now, let's try to apply this function. Okay, and so we write now an instruction like, just 1 second, I want to open a text editor because I want to write the instruction while keeping the help visible. Okay, so the instruction that I have to write, it's something like P river flow, so probability of river flow is equal to PL norm, I open the parentheses, river flow, comma, mean log equal mean log maxan. Okay, comma, SD log equal to, SD is the R function for standard deviation, log maxan. Good. This is my instruction that I have to cut and paste into R, which is taken directly from here. You know, probability of river flow. Look, river flow is my step-by-step coverage of the range between 0 and 30,000. It's PL norm of river flow, which is my vector of step-by-step coverage from 0 to 30,000. And then the mean of the logarithm of my data. Maxan are my data, observed data. Okay, let's see if it works. I selected this instruction, copy. With the right, I copied it. I go into the R console. I go back here, paste. Good, I got it. So I suppose that P river flow is probability of not exceedance of river flow from 0 to 30,000. And let's check if what I obtained matches with my expectation. What I expect is that the probability of not exceedance of 0 is 0. This is what I expect, or very close to 0, what I expect really 0. And the probability of not exceedance of 30,000 should be very close to 1. very close to 1, because if you look at our series of annual maxima, let me plot it again. Plot max and I equal line. From this plot here, you see that indeed the max is about 18,000. So 30,000 is much more than the max. So the probability of not exceeding of 30,000 should be very close to 1. Okay, now let's look at the P river flow result, P river flow, but not the whole series of, okay, we can look at the whole series of 300 numbers. First of all, let's look at the highest value. It's very close to 1, is 0.9999, which is fine. It matches my expectation. Let's look at the first value. The first value is 0. Perfect. I think it is reasonable. It is reasonable. Let's plot, just to make another check, plot P river flow against river flow. Okay, type line. This is the cumulative probability distribution, which is okay. I mean, it's reasonable. It's reasonable. What you see here is that the probability of not exceedance starts from 0, increases rapidly up to a value of, let's say, 15,000, and then it's an asymptotic tendency to 1. This is fine. This is what we expect. It's a long tail. This is a very long tail. Okay. You may wonder, what is the density? Remember, this is cumulative probability. To compute the density, we should take the derivative. And the derivative, in this case, this function is described by discrete points. The derivative is just given by the difference. So we may do this in order to plot the density. Plot river flow, and I don't remember what is the R function for computing differences. I think it's diff, but let's see. And I suspect, let's see. Yeah, I suspect that I suspect that it will give an error, because when you compute differences, you have a reduced number of results. It's not more 300 or 1, but is 300. So let's do like this: river flow from 2 to 301. Because I need to reduce the length of river flow, because otherwise it doesn't match. Okay, now let's have a look at the result. This is the probability density, which looks fine. It's a long-tailed density distribution. I just want to make sure that you understood what I did. So what I did is, basically, let me just think how I can, let me open a graphic blackboard. I need to write with the mouse, so I hope that you are patient with me. Okay. So what I did is I had a probability distribution that was described, just 1 second. Okay, the pencil. Let me see if it works. Yeah, it works. So I had my cumulative probability, which was given by, again, be patient with my writing, because I'm writing with the mouse. So I had this, or let me just 1 second. 1 second. Let me try here. And I need to share the second screen. 1 second. Okay. Okay, and I need this one shared. Okay, I think you see it now. And now I should be able to use the pencil. Okay, what I had is, I think this is a little bit better. What I had is a cumulative distribution. So here I had the CDF, and here I had the river flow, okay? And what I had was from 0 to 1, something like this. Something like this, okay? Good. And then I wanted to compute the derivative with respect to the river flow of CDF, which is equal to the PDF, okay? PDF, it's equal to the density. But this function was described with sequence of segments. So this was indeed described by, let's say, a starting point, and then let me assume that it is described by 1, 1, 2, 3, 4, 5, 6, 7, 8 points. Okay, actually it was, in my case, it was described by 301 points, but let's suppose that they are 8. In order to compute the derivative, what I did was simply to compute for any value of the river flow for any of these 8 points, the difference delta between cumulative probability. So I compute this difference delta CDF. And I did this computation for every point. But if you have 8 points describing the function, the number of differences is 7. And therefore, when I passed to the PDF here, when I passed to the PDF, I wanted to put here the difference delta. I put it here in the vertical axis. And on the horizontal axis, I couldn't keep the same number of points, 8. I had to reduce the number to 7 because otherwise, of course, the length of the y coordinates is different with respect to the length of the x coordinates. So what I obtained was indeed this function here, but here I used the river flow from 2 to 301 because I had to reduce to discard the first river flow. Okay, and then if we go back here, this is why here I plotted the river flow from 2 to 301, and this is just the difference, the delta of the cumulative probability. The moral of the story is that if I look at this graph, it is reasonable, and just pay attention to the fact that I am making these checks precisely for the very reason that I want to make a check. Okay, so this probability density looks really fine. I mean, it is what I am expecting, and it means that in the vector P river flow, I have the desired probabilities. Okay, good. Now I have to estimate for each one of the river flows. I have the probability. Now I have to estimate the vulnerability and the exposure for each value of river flow. So I have to get back these two functions and describe them in numbers. Okay. So what I see here is that up to a value of 12,000, vulnerability is 0, and up to a value of 8,000, exposure is 0. But let's build vulnerability first, okay? And the vulnerability, then it's, let's call it vulnerability. Vulnerability. First, let's create the vector of vulnerabilities, and let's give them, all of them, the value of 0. Repetition 0, 301. 301 because 301 is the vector, the length of the vector of the river flow. So I want to create a vector of vulnerabilities by starting from 0, which is long, which has the same length as the vector of river flows. So this instruction means that I have a repetition of 0 for 301 times. If you type vulnerability now, you see it's a sequence of zeros. Okay, good. Let's just create the vector exposure at the same, in the same way, exposure. Very good.
Prof, why
Yeah.
301 for the river flow?
Because the river flow was generated with this instruction. Just 1 second. Sequence from 0 to 30,000 with step of 100. So if you start from 0, you get a sequence that is 301 long. Okay, if I started from 100, then of course I would get 300 numbers. But if you start from 0, let me just show you a very simple example. The sequence from 0 to 10 with step 1, it's 11 numbers because you count also the 0. I hope it's clear.
Yes, it is. I thought about 3,000, not 300, but it's okay.
Ah, okay. No, because if you go to 30,000, the step by 100 is 300, not 3,000.
Okay, it's clear.
Okay, thanks. No, I mean, these are doubts that need to be explored because, as I said, it is extremely important that you get the meaning. And if you don't get the meaning, it's not your fault. It means that there is something that I need to better explain. Okay, good. So vulnerability and exposures were created. This is fine, but vulnerability, now it is fine to have, let me just write it down again. It is fine to have 0 up to 12,000, okay, up to a river flow of 12,000. On the other hand, from 12,000 onwards, I have to make a linear interpolation, okay? So just 1 second, give me 1 second. I want to, okay, let me just forget about this. So up to what index I have to keep the value of 0? So let me just show you here. It's 0 up to a river flow of 12,000. And the value of 12,000 in the river flow, let me just show you the vector of the river flow. This is the vector of the river flow. 12,000 is reached at the index 121. So vulnerability must be 0 up to the index 121. From 122, which corresponds to a river flow of 12,100, to 18,000, 18 or 16, just let me see, 16,000. Just 1 second, I need to check. Vulnerability is 0 up to 12,000. No, it's 1 for a peak flow of 18,000. So from the index, let me go back here. From the index 122 to the index 181, I need to make a linear increase. Okay, let's make this linear increase. And from the index, as I said, 122 to the index 181. Okay, good. Now we have to write it in this way: vulnerability 122. Yeah, 181. Yeah, okay. It's equal to, let me think how to write this linear variation. We need to change to it a little bit. So this is equal to 0 plus 0 is the starting value plus it's the difference. The difference is of invulnerability that has to be reached between these two indexes is 1. So 1 divided by the number of indexes, which is 60, I think, times the index. How to do that? Okay, it's times sequence 160. Just 1 second, because maybe that I need, I think it's better to write a 4 cycle. Let me think if I can do something meaningful without making it too complicated. Let me just do it in this way, because actually I think there was a spelling error in vulnerability, but this is not the problem. I think it is more understandable for you if I make a cycle for E in 160. Yeah, 60. And then I open a square bracket, meaning that now I have to follow with the instructions for the 4th cycle. Okay. Let me write it down, and then if there are some doubts, you step in and you ask me. Vulnerability. I think here we have to write 121 plus I. So the index of the vector is increasing at any step of the 4th cycle. This is equal to 0 plus 1 divided 60, sorry, 60 times, I think it's just I minus 121. I think this should work, because at any step of the cycle, I is increasing of 1. So at the first step, we are changing the value of vulnerability index 122. At the second step, we change vulnerability 123, and so forth. And the value that we give is equal to 0, the starting value, plus 1 over 60. 1 is the change in vulnerability, the total change. We need to divide it by the number of time steps, 60. And then this step change at any time step has to be multiplied by I minus 121. This is not correct, or I would say that here we have to write it's I minus just 1 second. I is okay. It's 121 plus I minus 121. I think in this way it should work. Let's see. Okay, let's see if it works. So I got a result here. Let's plot vulnerability and see what happened. I am expecting from the plot that is 0 up to 12,000, and it reaches 1 for a river flow of 18,000. Let's see, plot vulnerability type equal line. Let's see the plot. Okay, this is good. This is good because, okay, the index here is not river flow. Let's plot vulnerability against river flow, because otherwise we don't understand river flow. Okay, here is the plot. I think it is correct. Of course, now we need to take care of the part from 18,000 to 30,000. It's not finished. Now let me finish then. So now it is very simple. Vulnerability. Vulnerability 8,000. So 182 to 301 is equal 1. Good. Let's make the plot again, and then we discuss. Now it is precisely what I wanted to get. So here is the plot, and here is the sequence of function that I used for making the interpolation from the fourth cycle to the remaining part. Let me show the plot again. Questions? Because these parts are very useful for us in order to understand how to code, how to make programs. Questions, please. If you have anything that you didn't understand. Okay, no questions. Let me start. Let me just include in the chat a pool. It's anonymous, don't worry. Let's hope that, okay, pool.
Could you repeat later the passage about the creation of the vector of vulnerability?
Sorry, because I couldn't get, can you repeat the question? Because it was not clear,
Yes.
the audio. Yeah?
Could you repeat the passage of the creation of the
Yeah.
vulnerability vector?
Okay, I repeat the steps one by one. Okay, and let's keep the final result here. And let me just see. I want to fit both the console and the plot window into the same screen. Okay, good. Okay, let's keep the final result here, okay? Because this is what we need to create. And basically, I created it numerically with a sequence of points from river flow 0 to river flow 30,000 with a step of 100. Okay, so first of all, I created the river flow, and let me just go back because I want to make sure that river flow. I created the sequence of the river flow, sequence from 0 to 30,000 with a step of 100. And this makes 301 numbers. Okay, now I have to create the vulnerability. For now, I just created the horizontal axis of this plot. And now I have to create the coordinates of vulnerability. It is very easy up to the value of river flow 12,000, which corresponds to the river flow index 121. So up to the river flow value of 12,000, I put zeros. But first, let me create the vector of vulnerability with all zeros. Okay, let's create this vector. Okay, for now I have created a vector of zeros. Okay, and let's write on the plot what I have created. Lines vulnerability. Lines, sorry, river flow vulnerability. And let's put the color red, color equal red. So you see on the plot what I have created is a line of zeros. Okay, this is fine up to the index 121. And then from the index 121 to the index 181, sorry, I need to make the linear increase of vulnerability from 0 to 1. I decided to use a 4 cycle, so to change the values one by one. Okay, so 4 cycle. I understand these are steps that need to be carefully explained. The 4 cycle is the cycle is a way to make a repeated operation. Okay, I want to repeat it 60 times because I want to change vulnerability from the index 122 to the index 181 60 times. I open a curly bracket because when I have, let me see if I need the curly bracket. No, I don't need it. I can, this is the instruction to be repeated 60 times. The instruction says that at each step, for each I value, I have to change the value of vulnerability at the index 121 plus I. So let's suppose first cycle, I is equal 1. Then the instruction says that vulnerability 122, the first value to change, is equal to 0, starting value, plus the delta of vulnerability at each value. It's 1/60 because the total delta of vulnerability is 1. I have to divide it by 60, which is the number of values that I have to change, the number of vulnerability values that I have to change. Okay, and this 1/60 I have to multiply by an increasing number which starts from 122 minus 121. For I equal 1, the ratio 1/60 is just multiplied by 1, which is a small delta from 0 to 1. And then for I equal 2, you increase this small delta linearly. Okay, and if you make this, and now you plot the line that I have obtained in blue, this is what we obtain. And you see that the blue line goes back to 0 because I still have to change the final part of the vulnerability curve. The final part is here. Vulnerability from 182 to 301 is 1. Good. And now you can plot again vulnerability, call the color we put orange, and the width of the line, let's make it twice. So this is the final result in orange, which is what we wanted to obtain. I hope it's clear. Any other question? I mean, now we have to make the same thing for exposure, with the difference that exposure is 0 up to 8,000, and then it varies linearly from 0 to 12 millions between 8,000 and 16,000. So what I have to do, it's precisely the same thing. Exposure was already created, but let's create it again. Exposure. Repetition 0, 301. And then the 4 cycle. Just 1 second. Where is the 4 cycle? Here it is. But here I have I have to keep 0 up. Okay, I have to keep exposure 0 up to 8,000, which is the index 81. And then the for cycle varies for 80 step, not 60. Now, let me get the linear interpolation. It's here. Exposure instead of vulnerability. Exposure. And this is from 81 plus, just 1 second. Yeah, 81 plus I. This is okay. Yeah. And then this is 0 plus 12 million. Let me just expand a little bit the console. 12 million divided by 80. And here I have to put 81 plus I minus 81. I think this is correct. Let's see. And then I have to keep the exposure, the final part, it's missing. Here, exposure. This is 162. Okay. It was not correct. Here it is. Let's plot exposure, see what happens. Plot exposure type equal line. Okay, I think it's, let's me plot exposure depending on river flow. Okay, good. I think it's fine. This is our exposure. Now we are almost done, because now what we just have to do is to compute the risk as, let me call it risk, is equal to probability. I called it probability. Let's see. Not probability, but P river flow. Sorry. P river flow. Risk uguale P, equal to P river flow times vulnerability times exposure. Fine. What are we expecting here? Let's try to imagine what I am expecting. And what I am expecting actually is something that it's 0 up to 12,000, because vulnerability is 0 up to 12,000. So I expect something that is 0 up to 12,000. I expect a max value of 12 millions, which probably it's not reached. We get very close to it, but it's not reached. It's not reached because probability is never 1. So it is the last result will be vulnerability 1, P river flow 0.9999, and exposure 12 million. So I expect something that is always increasing, okay? And so let's try to plot it. Plot river flow risk, and let's put it in red. And let's put a width of 2. Okay, type equal line, sorry. Type equal line. Okay, this is our result. This is correct, in my opinion. Why I say it's correct? I say that it's correct because we have a discontinuity at 12,000, which is fine. And then we have another discontinuity at 16,000 when the exposure becomes max. And then vulnerability is keeps increasing. And then at the value of 18,000, it is the value of 18,000. If we write a vertical line in correspondence of 18,000, we see that indeed it's at the value of 18,000, we are getting very close to 1, very close to 1. Even if it keeps increasing, if I put another horizontal line at 1, sorry, sorry, there is something here, h equal 1. Let me just see. Yeah, no, okay, I should have put 12 million. Okay, you see that the red line keeps increasing towards 12 million, which is the max that I was expecting. Okay, so I mean, it's okay. It's okay. It is what I was expecting. I would say that it matches my expectation. On the other hand, let me go back to the curves that I have shown to you at the end of the lecture. It's not what is depicted here. It's not what is depicted here. Because here I depicted a yellow curve that reached the max for risk. What I have here is something that is asymptotically tending to a max. So let's read the final question of the exercise. Make a reasoning on the meaning of the obtained risk values. What do they mean? This is an interesting question. And I have a proposal for you. This is an interesting question, which is not easy. It's not easy, okay? And the answer is related to the difference between probability mass. Remember, when we talk about rolling a dice, it is the easy case of a discrete random variable. And the value of probability that I plugged into this equation in that case was, for instance, the probability of getting 6, not the probability of not exceedance. It was the probability of getting 6. And in this case, I obtain a curve that indeed may behave like the yellow one that you see here. Okay. I called it probability mass for the case of integer variables. And then for real variables, we talked about cumulative probability and probability density. So the reply to this question is related to this nodal point. Okay. So here we used the cumulative probability. Okay. And in fact, for each peak flow, we use the probability of not exceedance to estimate P. This is the key for replying my question. But still, we didn't discuss the meaning of the obtained values, the meaning of this graph. What is the meaning then? What is the difference with the graph that I plotted on my web page in terms of meaning? Okay. Now, I propose that on Monday in the class, we open a discussion on this. The reply will not make our exercise tougher. The exercise is done. Is done. If you understood, how it works, give me 1 second. I'm sorry because I got a call and I have to reply. Give me 1 second. sorry for that. Okay, so as I said, I would like to start this discussion next time. And I would like also to give you a homework. Try to think at it, okay? It would be very nice to make a comparison of your ideas, because this is a very important and final step in our discussion on risk estimation. It's not yet on the in my web pages, but I will add it. I will add the result of our discussion later on. Okay, do you have any question? One second, I share my screen and I stop the recorder. So maybe that if you have some questions, you feel less shy if I stop the recording.